Everybody. I wanted to give you a brief overview of Hamming codes. The Hamming code system is a system that allows you to create matrices to do error correcting codes. The 7-4 Hamming code contains 4 message bits, 7 code word bits, and 3 check bits. And this is characteristic of NM linear block codes. K, the number of check bits, is greater than or equal to 3 with Hamming codes. And this leads to some redundancy, R, where you compute the redundancy by the total number of bits in the code word, N, and divide by the total number of bits in the message, M. So, for example, in the 7-4 Hamming code, we have 7 bits in the code word, that's N, divided by 4 bits in the message, that's M. And so we have 7 divided by 4, and that is the redundancy. The minimum number of bits that we require in a Hamming code is 3, and this enables us to do single error correction or double error detection. And so let's see if we can run through an example where the number of check bits is equal to 3, the number of message bits is 4, and the number of code word bits is 7. So this is a 7-4 Hamming code, and thus message bits plus code word bits, 4 plus 3 is going to be 7. We create what's known as a parity matrix. The parity submatrix uses a so-called Hamming rule. We let the M rows, there'll be one parity row for every message bit, have all 3 bit words. So you're going to have 3 check bits for each parity row. And you're going to have 3-bit words with 2 or more ones in any order. And what you'll do is you'll create the so-called generator matrix, and that'll be an M by M identity matrix with the P matrix submatrix next to it. And so what we'll see is here's the M by M identity matrix, and that's a 4 by 4 identity matrix. And then we go on over here and we can see the 3 by 4, or maybe the number of rows is first, so we say 4 by 3 P matrix. So if we go back to the generator and say, look, we're going to add a 4 by 4 to a 4 by 3, that's going to give us a 4 by 7 total matrix. That'll be the generator. And so if we go in over to follow this example, here's the generator identity matrix adjoined with the parity matrix, giving us the 4 by 7 matrix. And so the N by M, that's number of code word bits by number of message bits, in the generator matrix is what characterizes the NM Hamming code. So we can run this example using 4 bits for the 7-4 code message, and C will be what's called the block for the check bits. And so there'll be 3 check bits, that is 7 code bits minus 4 message bits for the 7-4 code. And what we'll do is we'll create a code vector of n bits, which consists of the message plus the check bits. Now we would like to use a code vector x in order to do our transmission, and to make that transmission robust in the face of noise. So what we'll do in order to do that is we'll take the message, which is 4 bits, multiply by the 4 by 7 generator. So we've got a 1 by 4 times a 4 by 7, and that'll give us a 1 by 7. And that multiplication will occur using modulo 2 arithmetic. That is to say, we're going to use bitwise exclusive OR. So here's the 1 by 4 times the times the 4 by 3. That'll give us a 1 by 3. That's if you do the message times the parity. But if you do the message times the generator, you'll get a code word. So we have a so-called check vector, which is used for decoding, and all we need there is the parity matrix and the message, and we can obtain a so-called check vector. So first thing we want to do is establish the weight of each one of the code words, and the weight is obtained by counting the total number of ones in the vector. So this is a scalar, positive integer, which can be 0, and the total number of bits that we were going to count up to here, this is 3. We can keep going. We can get 4 bits going in this, but we stopped at 3. And here are the check bits. And so this is the first 8 of the 16 code words used to compute the table. So now if we want to obtain a transmitted code word and then take a look at what we actually received after some distortion, we assume that x is not equal to y. That is, you transmit something, but it's not what came out, because we have a so-called noisy channel. So let's run through the example. We'll take the P matrix and we'll put it on top of the identity matrix, and we'll create what's known as a Hamming matrix that's been transposed. So here's the identity matrix on the bottom, and here's a P matrix up on top. And if you multiply the code word times the H transpose, it should be 0 when there's no errors, provided that X is an appropriate code word. So let's take a look at why that should be true. We use the generator in order to create the code word, and now we're using the transpose of the generator in order to do the decode. So now let's take a look at the error. Error is going to be a single bit error is going to be a vector, which is then exclusive ORed with the code word in order to cause a bit flip. So here comes the a single bit. If it is exclusive ORed with a 1, it's going to take that 1 and turn it to a 0. If it's exclusive ORed with a 0, it'll take the 0 and turn it into a 1. Similarly, if you want to do the inverse, you can take the output and you can exclusive OR it with the error, and you'll get back to your original code word, right? So exclusive OR is an invertible operation. And when you take the original code word and you multiply it by the H matrix transposed, you get what's called the syndrome. And the error is going to be equal to a function of the syndrome, and you'll use a syndrome table lookup to determine where the error occurred. And once you know where the error occurred, all you need to do is flip the bit back and you get the original vector. And so what we find is that because of the exclusive OR operation inverts itself, that is, E exclusive OR with X gives you something that is Y. If you take Y and exclusive OR with E, it's going to give you X. You can use anything that can decode where the error occurred to get back to your original vector. So syndrome depends only on the error vector, and the error vector is computed. And the computation occurs in this way. We take a one-row 0 matrix, adjoin it with the H transpose matrix, and you're going to get yourself a syndrome. And the syndrome, once you have it, is going to give us an indication as to where the error occurs. Once we know that, we can compute the original code word at the receiver, and we do that by taking the original code word, multiplying, well, the received code word, we're multiplying it by the H transpose matrix, getting our syndrome, and finding out where the error occurs. That allows us to invert. So here comes the example. we've got a received code word, y. We multiply it by H transpose. You can see the identity matrix in here. You can see the parity matrix over in there. So all you need at the receiver is an identity matrix and a parity matrix. You multiply the received code word, and then you can do this. Take this row, multiply it by this column. There's the 110100, 110100. Here's the original code word. Now you're going to do the bitwise exclusive OR. You get a 1. You do the same thing with the next column. Take this column here, which is column 2, and then you do a exclusive OR bitwise multiply, and you get yet another code word, 1. Now you do the same thing in here. You do the bitwise multiply, and then you do a exclusive OR addition, modulo addition, and you get 0. And now you have a syndrome, 110. Here comes your syndrome, 110, and you can look that up. 110 says we've got a bit error in the third bit of the code word. So here comes the third bit of the code word. Here's the original code word. We exclusive OR these two things together, and we get the original transmitted vector. And that's how you do Hamming decodes. And I hope you liked my little presentation. Thank you.